Hello, I'm Tim McComb, and I'd like to welcome you to the first in our series of webinars on improving EV battery welding. Today, we're going to be joined by Jeff Franks, a Director of Marketing, who will tell you about our solutions for reliable, high-volume welding. Before we begin, I just want to have a few housekeeping items. For those of you joining us on the Goldcast platform, you can ask your questions in the chat off to the right-hand side. And for those of you on LinkedIn and YouTube, please ask your questions as well in your respective chats, and we'll get them all gathered up together and answer them and get to as many of them as we can before the end of our time slot. When Jeff is finished, we'll also have a brief poll while we gather the questions, and then we'll go into a live question and answers. Finally, I'd like to also invite you to our next session, which will be on May 7th, if you'd like to also learn about dissimilar materials welding. And so with that, I'll pass it over to you, Jeff.
Many thanks, Tim. And a warm welcome to everyone who's joining the webinar on EV battery welding today. Please allow me to take a minute to introduce myself. My name is Jeff Franks, and I have been working in the industrial laser industry for well over 25 years, with the last 10 of them at Coherent. Over the years, I've worked for several different industry-leading companies, as well as on multiple continents, which has furnished me with a good insight to numerous technologies and also varied manufacturing philosophies, though always with a strong emphasis about the automotive and machine tool sectors. Onto the topic: reliable, high-volume production with lasers. I would like to give my very warm thanks to the team at Coherent for making all the arrangements for today's webinar and for reaching out to all of you. As I'm sure you can't help reading every day, the global market for EVs is extremely dynamic, and Coherent is right there at the forefront, servicing some of the industry's most demanding and famous customers for high-volume manufacturing. The intersection of modern EVs with the laser precision manufacturing is plentiful with applications. The infographic nicely shows just how integral lasers are to modern EV manufacturing, and starts with the backbone of body-in-white applications, including hang-on parts such as doors and tailgates. The partially completed car body then meets with some type of battery pack in their various formats, and with the rest of the EV powertrain, including inverters, traction motors, right through to Tier 1 e-axles, depending on the manufacturer. Fortunately, there are a great many laser application steps that bring us up to this point. And this is driving growth in the automotive manufacturing market for high-power laser companies. Following this, there are still numerous and well-known downstream laser applications applied until a vehicle finally rolls off the production line. Lasers are really an enabling technology that, when executed correctly, helps to lift productivity and reliability for automotive OEMs. The exacting requirements for modern electric vehicles have resulted in the latest laser welding packages being employed to great effect across a wide variety of applications, from high-volume battery cell manufacturing through to battery pack assembly, and encompassing the many and varied EV powertrain applications. For today's webinar, we'd like to focus attention onto the example of contemporary EV battery pack busbar welding, though the same technology can equally be applied to all the applications mentioned here. Growing consumer demand for more convenient and compelling EV ownership has driven demand for faster and faster charging rates. Accordingly, battery pack bus bars are required to handle higher and higher current loads. Automotive OEMs must consider 4 key points for battery pack interconnect design: high current capability, high voltage operation, thermal stress, and environmental vibration. Smart product design needs to ensure these power distribution systems meet the principal challenge to minimize overall electrical resistance, keeping losses and heat generation to a minimum. 400 volts is still the high volume market choice, and with pressure to further reduce costs, is likely to remain so for now. Though, of course, more exotic, high performance and luxury vehicles are employing more costly, higher voltage systems. Conventionally, high current carrying bus bars and other high current devices have often relied on mechanical connections. These typically result in quite expensive, material intensive, and heavy joints. Laser welding offers many advantages with lower material content, reduced weight, improved electrical resistance, and high-speed, automated non-contact manufacturing. Unfortunately, laser welding of copper has historically often proved challenging due to its high initial reflectivity to standard laser wavelengths, which resulted in poor quality weld seams or with pores and spatter defects. For engineering teams, busbar interconnects are a system critical point for losses and heat generation, and any process needs to reliably produce high-performance joints day in, day out. Coherent is in the enviable position of arguably having the broadest portfolio in the photonics industry today. This results in us being truly, fully vertical and able to offer complete, co-engineered welding packages for the automotive industry. These types of packages are fully integrated with all hard and software developed in unison. They must combine industry-leading products for laser source, process head, machine vision, and process monitoring into one outstanding welding package. We will examine how the combination of the latest ring and center mode beam technology fiber lasers can be integrated seamlessly with the latest remote scanner welding technology, which in turn integrates vision and process monitoring capabilities into one impressive welding solution. I'd like to start by looking at modern contemporary fiber laser sources and the complementary scanner process heads in more detail. Coherent's ARM laser is the absolute pioneer of separately addressable ring and center beam fiber lasers. We have been innovating these products since 2016 and continue to lead the way with new beam profiles and configurations optimized to produce ever higher penetration and into highly reflective materials or even faster process speeds. It was quickly recognized that the issue with other high brightness IR lasers could be overcome by employing our patented independently controllable ring beam, which can suppress patter and pore production through preheating and extension of the melt pool behind the keyhole. The process is also uniquely advanced by employing closed-loop power control to give an extremely stable and repeatable process, which even allows for power control down to as little as 1%. This fine control offers the possibility to have complete adjustment at the start and finish of the weld process, further suppressing spatter and pore production. Combining the latest ring mode fiber lasers with next generation scanners optimized to work at their innovative beam profiles produces a truly formidable welding package. Modern high-power remote welding scanners consist of two major variants, with 3D, or if not required, just 2D capability. In our case, we have the ubiquitous and industry-proven RLSK, and its equally high-performance stablemate, the high-motion 2D. Both types offer large, practical field sizes with multiple optical configurations and high-speed response times. These types of heads must be ruggedly designed to withstand the toughest industrial environments day in, day out, all whilst operating at up to 8 kilowatts of continuous laser power. New optimized F-theta optics with advanced materials, which offer exceptional focusing performance and a stable process over the entire work area, are now beginning to appear. By employing these next-generation optics on scanners, there is little or no need to make complex compensations when operating towards the edge of the welding field. Happily, we can now offer our high-motion 2D Galva with two such new optical setups, with a 1.5 times magnification and an even smaller 1.3 times. Both retain a remarkably practical field size given the tight focus spot capable. The optics, which are engineered to minimize focal shift and be largely insensitive to back reflected laser light, enable absolutely similar beam profiles anywhere within the welding field. This ensures repeatable process results no matter where the laser beam is directed within that welding field. The control for the latest process heads have been developed to offer full compatibility with more common and advanced laser types, which may need dual independent power control, such as our arm laser, and naturally must offer both high speed and accurate control in X and Y and potentially Z planes. And of course, come complete with enhanced controls for modern wobble welding techniques. Here we see a recent example of the type of results that modern advanced welding packages can achieve, with a near 6 millimeters of penetration into copper, with little or no spatter or porosity. The setup in this case combines our arm fiber laser, operating with a combined 8 kilowatts across the ring and center beams, coupled with a high motion 2D scanner with a 1.5 times magnification. Dynamic beam wobbling is also employed to produce an impressive joint specification. As prefaced, all the technology can be equally applied to many EV applications for automotive manufacturing, from electrical connections of silicon carbide devices on inverters to traction motor assembly with hairpin welding, as well, of course, the large number of joining applications used for battery cell manufacturing with both copper and aluminium materials. Heat input minimization is assisted by tighter spot sizes, especially, for example, on large format cylinder cells. In common with bus bars, the principal target for most powertrain applications is a high electrical performance for the joint. Now I'd like to turn our attention to integrated scanner vision systems. The latest vision systems available today offer extremely versatile hardware and software bundles, which are seamlessly integrated into the scanner control software for an intuitive user experience. They need to combine lightning fast positioning with flexible edge and shape detection to be well suited to battery can applications, and offer some advanced functions such as customized hairpin detection for that particularly demanding application. This enables high-speed detection of gaps between pins and allows for adjustment of the laser beam path to compensate. Whilst many busbar geometries employ overlap welding, we also see designs where the electrical connection needs to be made on a cutout edge, as shown in the short video. This is where high-speed pattern recognition functions can offer great value and really lift productivity. It can also be adapted to handle a wide range of product variants on a single production line or station due to the flexibility and range of shapes that can be defined. The final part of any comprehensive laser welding package today relates to a process weld monitoring package. The latest process monitoring systems need to consist of a versatile, hard and software package that should be able to cover welding, cutting, and even marking applications. They should also offer extremely high sampling rates with high sensitivity. Pulsed and continuous wave lasers at both high and low power levels must be catered for and should utilize a variety of different sensors, including both optical and even acoustic types. The very latest generation of softwares on the market are now employing AI neural networks to go beyond conventional okay, not okay classifications and can determine a defined mode of failure probability to the system and the end user. For the last section, I would like to examine a case study demonstrating how these modern packages work together in unison to bring value to customers. We selected some typical copper material to weld in a generic overlap busbar configuration with our highlight FL-arm and high motion 2D package, and introduce increasing gaps or gap faults in the range of 0.1 to 0.2 millimeters to the part setup to demonstrate how the SmartSense Plus process monitoring would track and classify the weld results. The teaching and setup flow for the system is broken down on the right side of the slide, beginning with the initial configuration of the sensors and then the collection of several data sets which enable the software to create the signal pathway. Once this is done, then the system is ready to collect the welding data and to either give pass or fail results, as shown in this case, or to add a second stage, offer our more advanced AI neural network to generate a defined mode of failure probability. The colors for the pathway are categorized as follows. Blue represents, in this case, an overlap of accumulated good signal data. Reaching either of the yellow bands would trigger a warning condition for the monitoring, the sensitivity of which can be adjusted, whilst going beyond the red would initiate an error signal from the software. The white signal on the pathway monitor is an example set of data, in this case for a bad weld or failure condition. When the pathway becomes very broad, as for example with wobble welding, then the average monitor can be utilized to enable a more stable monitoring of the process. Okay, we begin with a captured data set from a good setup with zero gap between the parts, and in this case, no dynamic beam movement, no wobbling. We can see how the white signal data stays well within the warning yellow bands and is generally even within the blue overlap taut dataset. The resulting weld is poor and spatter-free and has a weld penetration of over 0.5 millimeter into the lower workpiece. As we introduce a gap, in this case of 0.13 millimeters, we can immediately see the process or visible signals dropping low, whilst the back reflected laser light generates a clear error condition breach at that wavelength. As less power gets coupled into the weld, the temperature wavelength signals drop below their lower warning threshold. Whilst the weld may still produce a reasonable connection, the performance would certainly be below that of the zero gap condition. Here, we can look at the same process results with zero gap condition, showing some localized defects. SmartSense Plus has detected some spike conditions out of range caused by the creation of some small spatter defects in the weld. This could indicate poor generation inside the weld bead and should require further inspection by the end user. Now, we see how the process monitoring handles under the more challenging dynamic beam wobbling process condition. This increases the overall process window, no doubt, but also generates a wider band of pathway data due to the increased noise, which means that SmartSense Plus needs to be adapted for the warning and error condition limits accordingly. By applying the average monitoring filter to the noisy data, as we mentioned, we can provide more stable monitoring of the process. Now we can see the effect when we reintroduce the gap condition to the wobbling process, in this case 0.1 millimeters. We observed the wider warning conditions for the process and back reflection data were breached, and that in the actual weld, some pores started to be generated, although the top surface appears well. We see again that the weld process data is more stable and clearer when the average monitor filter is applied. Finally, the gap has now been increased to 0.2 millimeters, though other conditions remained unchanged. All signals have passed the error condition, and a weld joint was not created due to no energy transfer into the lower 1 millimeter copper plate. And as again, we see the corresponding data when shown through the average monitor. In summary, the latest generation of advanced high-power IR fiber laser welding packages offer excellent weld quality, even for highly reflective materials such as copper and aluminium. Ring mode fiber lasers, such as a Coherent arm with optimal closed-loop power control, which can heavily suppress or eliminate splatter issues. Process monitoring has become more and more usable in real-world production, especially now with the latest versions which employ AI neural networks to assess modes of failure probabilities. The latest generation of optics developed for some advanced scanners can now offer much tighter focus spots, which is ideal for copper welding. These optics are optimized to avoid distortion for repeatable beam characteristics anywhere in their generous welding envelopes. High speed and highly reliable vision systems are fully integrated into the overall software for optimized user experience. All of these technologies are available from one company, engineered from the outset to work together as a cohesive package from Coherent. Many thanks for your attention, and now back over to Tim for a roundup and the Q&A session.
Thanks, Jeff. That was a great talk. While we're gathering the questions for the Q&A, let's have a brief poll. We'd love to learn a bit about what kind of batteries everyone's working with. So if you could pull the poll up, that would be great. Let's see if, again, I should say for those of you watching on LinkedIn or YouTube, the poll won't work for you, but you will see the results on the screen here. So we're looking for what kind of cells you're looking at in your next project or application. Pretty reasonably even split between cylindrical, prismatic, and pouch so far. Let's see if it changes in a few more seconds, but it looks to be, Jeff, what would you say, relatively reflective of the reality in terms of what we see out in the market, that it's a pretty even split among all the different kinds of cells?
Yeah, I would say it's interesting that the pouch is actually a little bit higher than I would have expected, but yeah, the overall, all the technologies have their strengths, and we're seeing cylindrical increasing a great deal, and sort of enlarging its share of the market today. But I would have thought prismatic is today in production is still the largest, but we're talking about the next project. So yeah, this is probably indicative of what we.
Yeah, it's a nice snapshot of where things are going, perhaps. Mm-hmm. Okay, great. I think that's all the poll answers we're going to get at this time. So let's pull that down and start up with the question and answers. So let's kick it off, perhaps with a bit of a technical question. What are the thermal effects or the impact on the performance of the lenses from low to high power operation? So do we expect to see any sort of focal shift or anything like that in our lenses, or is that something we're designing?
for our lenses, I mean, and for I guess the next generation of lenses that we're seeing in scanners in the market, this is really, we can speak for our own products, but it's really been optimized to minimize that any kind of focus shift. So the scanner can operate from a kilowatt or even below a kilowatt up to 8 kilowatts with a real minimal effect. I would say not no effect, but almost minimal effect, so that we can see this really consistent profile wherever and however we're using the product.
Okay.
It's all down to the materials and design, really. Sorry.
Sure, that makes sense. I have a couple of questions that are similar. They're both about the working field area. So how can the larger working field really save process time? What are the things that that helps out with in production?
Well, it comes down to, that comes down to simply the repositioning times and what are the actual customer setup that they have, the final configuration and how they're using it. So if we're doing, if we're repositioning the galvo field for working over a larger area, then by having a larger galvo field, we can minimize the number of repositioning moves for the production process.
Okay. Here's a great question from Ibrahim at Southern Methodist University regarding the thickness of the busbar and tab materials in the real world. What sort of range are we talking about, so that they sort of have some reference for when they do lab work?
I think, typically what we see in our labs and from customer side is in the range of 1 millimeter up to 3 millimeters for a sort of what we call like four-wheel EVs. If you talk about two-wheel and three-wheel EVs, maybe the materials get a little bit smaller. We have seen on odd occasion materials up to 5 or 6 millimeters, and that's kind of they're outliers. And that's when customers come to people like Coherent and really want to see if they can weld these customer specific unusual ones. But 1 to 3 millimeters, that's the typical range.
Okay. Here's a question from David. Can you give any insight on the sort of complete cycle time for busbar welding on a cylindrical pack? I guess we didn't specify how many cells in the pack, but if you've got any insights on the typical weld time, how many cells are in a typical pack, and then how much do you spend on the process monitoring versus the weld process?
It really depends on the setup that the customers have. I mean, we've done a lot of modeling because obviously when we try to look at the market sizes and we see a lot of variance between configurations. So I wouldn't be able to sort of pull a number out. It's very varied from customer to customer and application to application or setup. What was the other part of the question?
And then relative to the weld process itself, what do you spend on process monitoring at the end of the process?
Well, the process monitoring, I mean, it's been, traditionally a lot of, in terms of time or cost. We talk about cost, right?
I think in terms of time. So it's basically something that they're doing every single weld and spitting out at the end of the process, or is it sort of?
Well, the live monitoring is happening. The live monitoring is happening during the weld process, so there's no additional time required. I mean, if you want to do offline post-process monitoring, that's a separate thing which can be done, but that's not what we've talked about in this particular talk. I mean, there are camera-based systems that look at the weld bead, and you can make those assessments after the weld, but that's a different point.
That makes sense. And I guess in terms of cylindrical cells, it's also depending on whether you're welding one cell at a time with a gantry style system, or whether you're using a scanner trying to weld a number of different cells within the field of the scanner and then moving the laser. So you can have a lot of different configurations depending on what you're trying to achieve. Yeah. Here's another. Go ahead, Jeff. Sorry, were you going to say something?
Yeah, absolutely. Agree.
Here's a question from Andreas. What are the typical vision processing times per weld location? And then what kind of accuracy is achievable in the real world?
Oh, that's very specific. I would have to defer to our product managers in that area. I mean, I don't know, Tim. I mean, we're certainly talking overall times in the millisecond range, but I'd need to get some more specific information. I mean, I know that for the most critical applications, it's really it has to be very, very fast, especially when you're doing many welds. Yeah.
Exactly. It can become a substantial part of your cycle time if you're not careful, because the welds themselves are only a few portions of a second long in most cases. So you can't spend a lot of time.
Potentially the vision system will be the slowest thing happening.
Yeah, exactly. And so that also, in terms of accuracy, you can get very accurate, but there's a trade between accuracy and processing time. And so there's a trade there. And I think an interesting thing there also that we sometimes see is that the alignment tolerance or the mechanical tolerances of your parts can lead into what sort of accuracy you need in the vision system. So sometimes you can decide whether you want to spend the extra effort getting the parts at higher tolerances, and then the sort of accuracy requirements drop on the vision system.
With hairpin welding is one of the most demanding applications for that, and we've seen that the times have dropped substantially from early days, from when the vision systems were out there trying to do that, and customer needs and requirements have pushed the times down dramatically.
Here's another one. What is commonly the biggest variable contributing to poor aluminum to aluminum welds? So what's the sort of typical thing that goes wrong in those welds?
Well, surface preparation is very important, or the consistency of surface preparation. So some customers will employ other processes to make sure that there's a very consistent surface preparation. If we're talking about cast material, then there's a lot of room for issues around that. So we have to be very careful to optimize the process to make sure any porosity is not occurring, or it will occur, but is minimized, and particularly on the surface of the material. You don't want any pores or roughness on the surface of the material, which could affect the durability of the joint.
Sure. And then along similar lines, in terms of defects we're trying to compensate, what's any thoughts on sort of the maximum gap that we can bridge between the tab and the bus bar when you're welding? Or is this varying from process to process, I guess? Or
well, this is there's a sort of classic 10% but margin, or this material like that you can. That's the sort of guideline of what you can do. It's possible to stretch it a little bit further, but then you start to really affect the electrical properties of the weld and the performance of the joint. So typically around about when we saw on the examples that 0.1 of a millimeter with 1 millimeter material, we still got a reasonable weld connection, although SmartSense Plus told us that it wasn't as good, or had some reduction in the quality of the joint compared to a zero gap tolerance.
Sure. And since you mentioned SmartSense Plus, a quick question from Ted here was, is the SmartSense Plus usable on other brands' scanners, or is it required to be used on our internal scanners?
It is. That's a good question. I'm not sure commercially whether the product is something that was developed internally, and so far I think the application has only been on with Coherent hardware. Yeah, I'm not sure. Tim, do you have you seen it?
I think that's the case, because it runs on the same software as our scanner control software. But it's an interesting question, and we'd be happy to sort of start it offline.
Yeah. I guess there's no reason why it couldn't work with
right. Fundamentally, certainly it could be attached, but there's a question about software integration and everything that we have to address. Yeah. So if you're more interested, definitely reach out to us. Click the button up in the top corner there and request a laser consultation, and we'd be happy to talk about that. A follow-up question from Elliot Ash. Solidification cracking is a large issue with aluminum. Have we looked at all into wire additions to mitigate this problem with laser and wire-fed processes?
Yeah, absolutely. I think the focus on this presentation has been about remote scanning equipment rather than with a wire fed. So typically, we don't use a wire for remote welding. It would be quite challenging. But we definitely do use, and for certain applications, certain customers, we do use wire feeding to improve the overall quality of the weld and avoid cracking, depending on the aluminium alloy that's used. Yeah, absolutely.
Yeah, and that makes sense. Certainly in the context of bus bars, we're not going to see it, but perhaps in the battery housings or battery cases and things like that, we might see that kind of.
Yeah, and we see it with battery packs and even in body and white applications.
Mm-hmm. A question from Mehran, and I'm going to try to interpret this, but if I get it wrong, send another one. It says, how do you control the power on the bend? I think that means power on the fly, is what I'm guessing. So can you control the laser power while you're doing the weld with the scanner and laser sort of in concert?
Yeah, absolutely. So, I mean, we've got full control of laser power, both in the ring and the core. When we talk about ring mode lasers or in the single mode lasers, it's also possible to couple and link the power control of the laser with the motion of the scanner. What we're trying to do, I think, in many ways, is to really keep that to a minimum with the sort of by having a very consistent weld spot throughout anywhere on the Galvo field. But if we do need to slow down for a particular feature or whatever, then yes, that can be directly linked and control and reduce laser power as required.
Mm-hmm. Here's a question from earlier on. You in your talk, you talked about managing back reflection or having insensitivity to back reflection for remote welding systems. Is this a property of the laser or of the scanner and the optics, or something we do in both aspects?
It's really everything. Yeah, I mean, so the whole system in all parts is optimized for back reflection insensitivity. I mean, we start with the laser. Our lasers have always been insensitive to back reflection, our fiber lasers, so we have that sort of built in and designed in with the laser. But I guess the biggest or the new thing here is that we've come up with this next generation of optics, and they are even further optimized to avoid that. So the whole package is designed to be insensitive to back reflection.
Okay. And then a follow-up to that. Let's see. I think sorry, I lost that question for a second. Here it is. Is it possible to have a system that changes the magnification sort of without changing the optics? So I guess this is sort of referring to some kind of zoom or mechanical motion of lenses inside the system.
Right. So yeah, we do have such a system available from, I think we have Coherent has, I'm sure there are other options on the market, but we have our own version of this, and it's a particularly neat version. And these, it's a zoom collimation, if you like. It's a patented system that we have. It's quite a little bit unique, but and that's able to do that. It's implemented on a lot of our heads. I think not maybe quite all of them, but it will be. If it's not, they'll be soon. So yeah, we have that on scanners and non-remote welding heads. It's available. Yeah.
Great. Then I guess along the lines of magnification, there's a question here about the really low magnification. So 1.3x is something that's kind of unique, I think, to some of our systems. What kind of applications are those most useful for with the really low mag?
Well, I mean, I guess this was developed with a pull from customer side. We wanted to go deeper into the copper welding. We needed to get high performance, so we needed to get a brighter laser source with a low NA and more power into the center of the beam. And so as to match that, we needed to get the nice tight focus with the scanner as well. So we had to, and the scanner was developed and designed to work with the laser hardware, as we talked about, sort of co-engineered, if you like. So they can work independently, but they're really designed to work great together.
Sure.
Yeah. So and yeah, the applications are deep copper welding, really. I mean, that's the driver. Sorry.
Here's a question that just came in from Andreas. Is it capable of detecting the Z direction surface? So is there sort of distance measurement capabilities in our systems?
Not with SmartSense Plus. No, that would require an additional some other additional hardware to be able to detect the Z position of the workpiece, if that's what they refer to.
Sure, but there are, I guess we do have the ability to integrate sensors that can do that distance measurement.
Absolutely. Yeah, they can be fed into the system. That's no problem. Yeah. Just
exactly. So we use a third party. Yeah, whatever preferred third party height sensor you use can talk to those scanners. Mm-hmm. Here's a follow-up question from Ted. Can the SmartSense Plus process monitor detect porosity or spatter? Or is that something we would use a different sensor for?
Well, that's what we talked about in the examples in the presentation. I mean, porosity obviously being below the surface normally, we did see that it picked up abnormalities and it was able to detect the porosity. It doesn't directly detect the pore, the hole inside, but it can detect an abnormality in the process, and when pores were occurring in that particular example. Spatter issues, definitely. I mean, that's clearly something that's happening on the surface of the weld, and SmartSense Plus is very capable of detecting those issues.
Okay, great. Another question from Terry, going back to the discussion about focal height or a height shift. How do we address that height variation? I guess that's partly through the zoom optics we already talked about, but I guess also with mechanical motion or the robot itself might address that as well.
Yeah, I mean, it's really a mixture. We work together with the customer to decide the best way to deal with that. I mean, there are mechanical ways of dealing with that, fixturing and making sure. Alternatively, if you're not able to control that mechanically with the fixturing, then we need to have that additional detection, and then we can use that Z shift to compensate.
Okay. Here's a question actually regarding the arm laser itself, and I think they're talking about here so the sort of typical can cap weld. So it says, what are some limitations that you've seen using the arm system for cell sealing welds? So I guess that's sort of can cap on cylindrical or on prismatic cells. Are there any sort of limitations to processes we've seen, or?
Not so far as far as I'm aware. I mean, so far the arm laser has done well with most materials presented to it, whether it's the different types of aluminium that we see from manufacturers through to steel and stainless steel. All of them seem to benefit from the arm laser so far. We've pushed it in as much as we can in all those directions. So so far we haven't seen. I don't know if you've heard of anything or any issues around that, but my knowledge. So far it's sort of produced a good performance all round, but obviously there'll be that one application that comes along that may not work. But today, as my understanding, can cap is something that the arm laser is really well suited for.
Yeah, I think I'd agree with that. Haven't seen too many that haven't been successful. It's more about optimizing the right arm laser, the right fiber combination. That's certainly something that we have to make sure we're working with correctly. Sometimes it's as simple as changing the ring to core ratio to really dramatically change the process performance.
That's part of our ability. That's something where we provide some secret or source or some know-how for the customers, and when they present the geometry and the materials, then we can determine which is the optimal arm laser setup. Yeah.
Exactly. That's why our applications labs exist. We want you to come and give us a problem, and then we'll figure out how to use our technology to solve it. Another question came in. Can we detect the weld penetration with our camera system or with the SmartSense Plus? I think we're talking about the penetration depth of the weld.
With SmartSense Plus, it's not designed to detect weld penetration. It's really a process monitoring system. A weld penetration system that requires a different sort of sensor arrangement, and maybe in the future we will look at implementing that with SmartSense Plus. I mean, the software is I guess capable of working with that, but it does require different hardware in terms of what sensors are attached to the system to do that.
Yeah, exactly. That would be a sort of a third-party sensor. We've certainly integrated those into these scanners. It's just not something that's a standard part of the SmartSense package.
Yeah, it's perhaps on the roadmap. We'd have to talk to the business unit.
Sure. There's a question from Ryan. Are there any features in the laser or the scanner that can help with predictive maintenance, sort of things along the lines of Industry 4.0?
Certainly, the laser has features that are built into it to feedback, and there's ideas around getting all of the information from each laser to feedback into a central system, which would potentially point out or predict any issues that we saw coming on the laser side. That really depends on customers' implementation and whether we have the features there in the lasers, but if they're able to use that in their environment, because some customers, their work environment has some restrictions around how much communication can be done from laser to laser and in the production floor.
Sure. And I imagine also this could be something you could get if you're using SmartSense Plus. So you could monitor the data coming in from a SmartSense Plus from process to process, from part to part, and perhaps predict from those results a trend in one way or the other that might imply dirty optics or a change in something in the process that you could investigate. So it wouldn't necessarily point you to the root cause, but it might point you in the direction of the right cell to go look at, or the right laser source to go look at.
Yeah. I mean, we certainly have. I mean, the AI function in SmartSense Plus, depending on how it's taught, is able to make probability judgments and predictions on things like contaminated optics. Mm-hmm. So, I mean, it'll look at a problem, and based on the data that comes off the process, we can apply it to the neural network that's built into the software, and then come up with that. Okay, this is the most likely cause of the fault is potentially contamination in the optic or part fit up on the weld and so on. So the various different causes of the error.
Great. These have been great questions. I think that has covered all the ones we have in here. So maybe I'll give everyone a minute or two more to see if any additional ones come in. Let me just scan one more time to make sure I didn't miss anybody's questions, but I think I've addressed them all. So one last call for any additional questions. We get a couple more. Look at that. Here's one from Terry. One last one. What's the highest wobble frequency we can do in the scanner that you talked about?
Well, depending on the scanner, I'd need to. I mean, we'd have to ask you to talk to a specialist and come back to us. I mean, I think it depends very much on the application as well. There are physical limits, of course, to the scanner and what oscillation it could achieve, but depending on which scanner type and how it was done, I think I'd rather defer that to. So please contact us, and we can give you a little bit more information as to
specific numbers. We can definitely give you, but there are basically, depending on the mirror size in these scanners, that's gonna sort of determine how fast we can wobble. And we've got ones that are designed specifically for extremely high wobble speeds, and then we've got ones that are more traditional scanners. So we can kind of cover the range, and that's where Coherent Labs comes in. And if you want to try these different kind of wobble processes, we can test them out for you.
Yeah, so I mean, it's about power handling as well. As you mentioned, the mirror sizes affect how much power we can handle, and therefore also all the oscillation rates and the frequencies that we can achieve.
Yeah, exactly. Great. Well, I think that does it for questions. So again, Jeff, this has been great. Thank you very much for your presentation and your question and answers.
Thank you very much.
Again, thanks to everyone here for attending. One more reminder, don't forget to come see our next webinar in this series on May 7th to learn about dissimilar welding. So with that, thank you all again, and have a great rest of your days.
Thank you very much. Thank you, everyone. Bye.